Hey guys, tonight we are going on a tour. Not the exciting, warp speed, look a black hole, kind of tour. No, tonight's journey is a little more domestic. A little closer to home. We're going to be taking a very, very slow look at the surprisingly boring problem of space junk. It's the cosmic equivalent of finally noticing the dust bunnies under the sofa, except the sofa is planet Earth. So make sure you've zipped up your thickest conceptual spacesuit, because while there's no real cold, the sheer stillness might give you a chill. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, while you're at it, drop your city and the time in the comments below. It's always nice to know where we're all drifting off from, scattered across our little blue and white marble. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. Imagine, for a moment, that you are floating. There is no up or down, just a gentle, perpetual sense of suspension. You're not inside a cramped capsule, you're out in the open, tethered to nothing but this quiet moment. Below you, the Earth hangs like a giant, silent ornament. It turns with an impossible, dreamlike slowness. You can see the curve of the planet, the thin, electric blue line of the atmosphere clinging to its edge like a fragile halo. It's the only thing separating the warm, living world from the cold, absolute blackness that surrounds you. You're in what's known as low Earth orbit, or LEO. It's a bustling cosmic neighborhood, relatively speaking, stretching from about 100 to 1,200 miles above the surface. To stay here, you have to move fast. Incredibly fast. About 17,500 miles per hour, to be precise. You're circling the entire planet once every 90 minutes. Yet, from your serene vantage point, it doesn't feel like speed. It feels like a constant, gentle fall, a state of forever tipping over the edge of the world but never, ever landing. This is the fundamental principle of an orbit, a perfect balance between forward momentum and the relentless pull of gravity. It's less like a rocket-powered sprint and more like the universe's most elegant, high-speed ballet. You watch as the sun glints off the Pacific, a dazzling expanse of liquid gold. You see the swirled, white patterns of weather systems, moving with a grace that belies the fury of the storms within them. Night falls not with a slow fade, but like a soft, dark curtain being drawn across the stage. The Terminator line, that ever-moving border between day and night, sweeps across the continents below. Cities bloom into life, intricate webs of light against the dark land masses. Tokyo, Paris, Cairo, they look like scattered diamonds on black velvet. It's peaceful up here. Utterly, profoundly silent. The kind of silence that's so deep, you feel it in your bones. And then, you see it. Out of the corner of your eye, a tiny glint of light. It's not a star. Stars don't move like that. It's not a meteor, either, those streak across the void and burn up in an instant of fleeting glory. This is different. It moves with a steady, determined pace, tracing a clean, predictable arc against the starfield. It's too slow, too deliberate. Too punctual. It's on a schedule, which is more than you can say for most terrestrial public transport. It catches the sun's light for a moment, shining with a brief, artificial intensity, and then fades back into the darkness as its angle changes. You dismiss it at first. A satellite, probably. There are thousands of them up here, doing their important work. Communication, navigation, weather forecasting, taking pictures of your neighbor's suspiciously pristine lawn. They are the busy, working bees of our orbital ecosystem. But as you continue to float, another 90 minutes pass, and there it is again. The same glint, in the same path. A tiny, lonely traveler on a fixed trajectory. This is your first encounter with a piece of space junk. It might be a bolt that came loose from a rocket stage in the 1970s. It could be a fleck of paint that chipped off the Space Shuttle Discovery. It's insignificant. It's trash. But up here, it has a strange kind of permanence. What's truly fascinating is how we even see it. Many of these objects are dark and non-reflective. But some, particularly pieces of insulation or white painted surfaces, have a very high albedo, that's the scientific term for how much light something reflects. A random piece of thermal blanket can be more reflective than certain types of rock, making it surprisingly easy for ground-based radar and telescopes to spot, despite being no bigger than your hand. It becomes an artificial star, a tiny beacon of our industrial legacy. It's one of the odder little facts of orbital mechanics. The visibility of space debris often has less to do with its size and more to do with its surface material and the angle of the sun. A large, dark piece of carbon fiber could be nearly invisible, while a tiny, shiny washer could light up like a firefly. As you track this one little speck, a quiet question forms in your mind. If you can see this one, how many more are there? That's where things get complicated. While space surveillance networks can track objects larger than a softball, numbering in the tens of thousands, the population of smaller debris is a source of continuous scientific debate. Some computational models, based on statistical analysis of impacts on return spacecraft, estimate there are hundreds of millions of pieces between a millimeter and a centimeter in size. Others argue the number could be even higher. The truth is, astronomers are still arguing over the exact quantity, because you can't count what you can't reliably see. It's like trying to count every grain of sand on a beach using only a pair of binoculars from a nearby cliff. You get a good idea of the big rocks, but the fine-grained details remain a statistical mystery. For now, though, you let that thought drift away. You focus back on your single, silent companion. It has its own life, its own orbit, its own story. It poses no immediate threat. It's just, there. A quiet, forgotten relic, endlessly circling the world that made it and then left it behind. It's the first subtle sign that our pristine, silent view from orbit isn't as untouched as it first appeared. That single piece of debris continues its silent, lonely patrol. It's a product of our modern age of spaceflight, sleek, small, and anonymous. But as you watch it, a thought drifts into your mind, soft as a nebula. It couldn't have started this way. This vast, invisible cloud of human artifacts had to begin somewhere. It began with the firsts. The first satellite, the first rocket stage left behind, the first mistake. You let your consciousness drift back in time, back to the dawn of the space age, when the sky above was truly, completely empty of our presence. The 1960s. The space race is in full, frantic swing. It's a time of heroic ambition, of slide rules and immense, building-sized computers, of brave people strapping themselves to the top of controlled explosions. The goal wasn't elegance or tidiness, the goal was to get there. To beat the other guy. To plant a flag, to take a step, to prove it could be done. And in this exhilarating, high-stakes rush, things were sometimes misplaced. Picture it, June 1965. You're floating alongside NASA astronaut Ed White during the Gemini 4 mission. He is the first American to perform a spacewalk, an extravehicular activity, or EVA. He's tethered to the capsule, a handheld maneuvering unit in his hand that looks charmingly like a space-age water pistol. He's giddy with the experience, describing the view as a million-dollar view. He's supposed to be out for just a few minutes, but he's having so much fun that he stays out longer. The whole world is holding its breath, listening to the crackle of his voice from the void. And in the process of maneuvering, or perhaps while getting back inside the cramped Gemini capsule, a spare thermal glove slips away. It's not a dramatic event. There's no sound, no clatter. Just a gentle, silent departure. A single, puffy, white glove begins its own, unscheduled mission. It tumbles end over end in the slowest of slow motion, a ghostly hand waving a long goodbye. For a little while, it keeps pace with the Gemini capsule, a phantom companion on its journey. It becomes, for a brief time, an unofficial satellite. It was even tracked from the ground. Can you imagine being the technician at the tracking station, tasked with cataloging a glove? It had its own designation, its own orbital parameters. It circled the Earth at 17,500 miles per hour, a lonely piece of cosmic laundry. This is one of the most charmingly weird facts of early space exploration. Some of the first pieces of junk weren't fragments of explosions, but ordinary, mundane items. The glove orbited for about a month before its trajectory finally decayed, and it fell back into the embrace of the atmosphere, burning up in a silent, unseen streak of light somewhere over the Pacific. A footnote in the grand story of spaceflight. And that glove was made of the typical stuff of the era. A mainstream fact of space hardware is that everything is a compromise between strength and weight. The outer layers of that glove, and the suits themselves, were made of woven nylon and aluminized mylar, materials you might find in a high-end camping tent today. They were designed to reflect thermal radiation and resist micrometeoroid impacts, not to last for centuries in orbit. This is why many of the earliest, softest pieces of junk are long gone. They were flimsy by design. But not everything was so soft. Let's drift forward in time a bit, to a more modern, but equally clumsy, moment. You're now floating alongside the Space Shuttle Discovery in 2006. Astronaut Piers Sellers is on a spacewalk, testing a new method for repairing the shuttle's heat shield. He's using a tool that is, essentially, a fancy spatula to apply a kind of heat-resistant goo. And in a moment that every single person who has ever worked on a car engine or dropped a screw behind a desk can relate to, he loses his grip. The spatula drifts away. Again, no drama. Just a silent, silver object, spinning slowly against the backdrop of the Earth. A $100 custom-made spatula, now an official piece of space debris with the catalog number 30776. It's a perfect, almost comical symbol of the problem. We've managed to litter the most majestic, pristine environment known to humanity with kitchen utensils. It's the sort of thing that makes you want to simultaneously laugh and sigh. The spatula, being more robust than the glove, stayed in orbit for several months before it too met a fiery end. The fate of these specific, famous objects leads to an interesting point of scientific uncertainty. While we know they re-entered the atmosphere, the science of predicting exactly when and where a piece of debris will fall is surprisingly tricky. Astronomers and engineers build complex models of orbital decay, but these models have to account for a host of chaotic variables. The Earth's upper atmosphere, for instance, isn't a static, uniform layer. It breathes. It swells and contracts based on the sun's activity. A solar flare can heat up the thermosphere, causing it to expand and create more drag on orbiting objects, speeding up their decay. Predicting this solar weather is notoriously difficult. So, while scientists can say with confidence that Ed White's glove burned up in July of 1965, they are still, to this day, debating the precise models that would tell you the exact time and place it vanished. Its final moment is lost to history, an estimate in a sea of variables. So now, as you float here, you are aware that this silent space is filled with ghosts. Not just the anonymous, modern specks, but the relics of those first, bold forays into the unknown. You can almost see them, a lost glove from Gemini, a forgotten wrench from an early satellite deployment, a camera that floated away from a careless astronaut. Each one was a testament not to failure, but to the messy, imperfect, and deeply human process of exploration. They are the initial, almost innocent-looking brushstrokes in a much larger, and much more complicated, painting that is still being created all around you. The memory of the lost glove and the drifting spatula fades, like old photographs. They were singular objects, almost characters in their own short stories. You could point to them, track them, even give them catalog numbers. They were knowable. But the nature of the problem you're observing is shifting. As you continue your slow, patient orbit, you begin to notice something different. It's no longer about individual, identifiable items. The problem is becoming more diffuse, more atmospheric. You drift over a region of space that looks, at first glance, completely empty. There are no defunct satellites tumbling end over end, no large, obvious pieces of machinery. But as the sun catches the void at just the right angle, you see it. A faint, almost imperceptible shimmer. It's like watching sunlight filter through a dusty room, revealing a million dancing motes of dust that were invisible just a moment before. Except this isn't dust. It's a vast, dispersed cloud of tiny, metallic flecks. This is the second generation of space junk. It's the result of larger objects breaking apart. You're witnessing the legacy of defunct satellites and spent rocket stages that have been left to their own devices for decades. A typical example of a large piece of junk is the second stage of a rocket. After a rocket launches, the first stage falls back to Earth. The second stage often carries the payload, the satellite, into its final orbit, gives it one last push, and then it's done. Its job is over. It's a massive, hollow aluminum tank, sometimes the size of a school bus, now completely inert and drifting aimlessly. Now, imagine one of these bus-sized cylinders, left in orbit in the 1980s. For years, it just tumbles along, a gentle giant on a predictable path. But it's not truly alone. It's exposed to the harsh realities of space. You have the extreme temperature swings, from scorching heat in direct sunlight to deep, cryogenic cold in shadow. This causes the metal to expand and contract, over and over, for decades. The metal fatigues, weakens. Any leftover fuel or pressurized gas inside the tanks can, after all this time, finally cause the structure to rupture. It doesn't explode in a fiery Hollywood sense. It's more of a quiet, forceful pop. A catastrophic outgassing. The once solid rocket stage fragments into thousands of pieces. Suddenly, one large, slow, predictable object becomes a cloud of thousands of smaller, faster, less predictable objects. They spray outwards from the point of rupture, each piece entering a slightly different orbit. Some are thrown into higher orbits, some into lower ones. Their paths cross and recross. You are floating through the ghostly aftermath of such an event. The sun glints off shards of aluminum, slivers of insulation, tiny fragments of wiring and circuit boards. They are too small to track individually from the ground, but they are here, a shimmering, persistent hazard. This leads us to a fascinatingly nerdy, and somewhat odd, piece of space trivia. It's called Project Westford. Back in the early 1960s, at the height of the Cold War, the U.S. military was worried that enemies could cut the undersea communication cables, isolating America. They needed a backup. Their solution was creative. The plan was to create an artificial ring of copper needles around the Earth to act as a passive radio reflector. In 1963, they launched a dispenser that released 480 million tiny copper dipoles, each one thinner than a human hair, into orbit. It worked, sort of. But the international astronomical community was furious. They argued, correctly, that it was a deliberate and massive act of orbital pollution. Most of these needles have since deorbited, but the incident stands as a bizarre monument to a time when deliberately creating a cloud of space junk was considered a good idea. Some scientists, however, still argue that clumps of these needles could persist in higher orbits for much, much longer than anticipated. The debate over whether any Westford clumps still exist is one of those niche, long-running arguments you only hear about at very specific scientific conferences. The transition from single objects to these ghostly clouds is a fundamental shift. A single, large object is a problem you can potentially solve. You can track it, maybe even plan a mission to deorbit it. But a cloud of millions of tiny, fast-moving shards? That's a different beast entirely. It's less like removing a single piece of litter and more like trying to filter the air itself. And the source of these clouds isn't always accidental decay. You float past another region, and your conceptual Geiger counter for debris starts clicking faster. Here, the shimmer is denser. This is the result of something more energetic. In 2007, a defunct Russian military satellite named Cosmos 2251 collided with a functioning Iridium communications satellite. The two objects, with a combined mass of over a ton, hit each other at a relative velocity of about 26,000 miles per hour. The result wasn't a pop. It was a hypervelocity impact. The energy released was immense, instantly vaporizing and shattering both satellites. You are now drifting through the consequences. The collision created a cloud of over 2,000 trackable pieces of debris and likely hundreds of thousands of smaller, untrackable ones. These fragments didn't stay in one place, they were blasted into a huge range of new orbits, spreading the problem far and wide. It was like two cars colliding on a highway, but instead of the wreckage staying on the road, it was flung across every lane in both directions for hundreds of miles. This event was a wake-up call. It demonstrated that satellites could, and would, crash into each other. It proved that the models predicting such collisions were no longer just theoretical. You can see the legacy of that single event right now. The cloud has dispersed over the years, thinned out by orbital mechanics, but it's still there. A permanent, shimmering memorial to a very bad day in orbit. It subtly changed the very texture of the space around you. It's no longer just about the ghosts of past missions, it's about the scars of past collisions, etched into the very fabric of near-Earth space. The silence feels a little different now. A little more cluttered. You've seen the lone relics and the ghostly clouds of fragments. Now, you start to perceive a sense of organization to the chaos. This isn't just a random junkyard. It's a junkyard with neighborhoods. As you continue your serene, 90-minute laps around the globe, you realize that the density and character of the debris changes depending on your altitude. You are now a cosmic urban planner, observing the invisible highways and byways of our orbital infrastructure, and noticing where the traffic jams are worst. Let's start where you are, in low Earth orbit, or LEO. This is the bustling downtown core of space. It's where the International Space Station lives, where most Earth observation satellites hang out, and where many communications constellations, like Starlink, are being built. It's desirable real estate because of its proximity to Earth. You get great views, and it takes less rocket fuel to get here. Because it's so busy, it's also the most cluttered region. The shimmering clouds from the Iridium-Cosmos collision are thickest here. The majority of all tracked debris objects are in LEO. Floating here, you can feel the faint, whisper-thin drag of the upper atmosphere. It's almost nothing, but it's the single most important janitor in this cosmic city. A well-known astronomical fact is that this atmospheric drag is what eventually cleans up LEO. For an object orbiting at, say, 250 miles up, the altitude of the ISS, drag will pull it down into a fiery re-entry within a few years, or sometimes even months. But as you go higher, the atmosphere becomes exponentially thinner. An object at 500 miles might stay up for decades. At 750 miles, it could be centuries. This is the slow, patient force of nature at work, but it works on its own schedule, which is far, far slower than our ability to add new junk. Now, let your perspective shift. You gently fire a conceptual thruster and begin to ascend, moving outwards, away from the Earth. You climb past the densest debris fields of LEO, through a relatively clear zone, and into a new, very different kind of neighborhood. You are now heading towards geostationary orbit, or GEO. It's a long way out, about 22,236 miles above the equator. The journey itself is quiet. The space between LEO and GEO is sometimes called the Great Orbital Void, relatively empty of both satellites and debris. As you approach GEO, the scene changes again. It's not a shimmering cloud of tiny fragments here. The problem is different. It's more stately. More like an elephant graveyard. The objects here are huge. These are the colossal communications and weather satellites of the 1980s and 90s. The reason this orbit is so special is a beautiful quirk of physics. At this specific altitude, a satellite's orbital period exactly matches the Earth's rotation, 23 hours, 56 minutes, and 4 seconds. From the ground, a satellite in GEO appears to hang motionless in the sky, making it perfect for broadcasting television signals or monitoring weather over a single continent. It's the ultimate orbital parking spot. Because this orbit is a thin, precious ring, it's managed more like a cosmic landlord-tenant association. There are international agreements. When a GEO satellite reaches the end of its life, it's required to use the last of its fuel to perform a final maneuver. It pushes itself a few hundred miles higher, into what's known as a graveyard orbit or disposal orbit. So, as you float just above the active GEO belt, you find yourself in a silent, slow-motion ballet of the dead. Giant, multi-ton satellites, some with solar panels still extended like broken wings, tumble through the void. They are perfectly preserved in the cold, vacuum of space, with no atmospheric drag to ever bring them down. They will be up here for thousands, maybe millions of years. They are silent monuments to our first global communication networks. Here's a bizarre little tidbit for you: some of these dead satellites aren't completely dead. They are sometimes referred to as zombie satellites. Occasionally, a stray signal or a short circuit can cause an old, abandoned satellite to start transmitting again, broadcasting nothing but static or garbled data, creating interference for its active neighbors. Engineers on the ground then have to play a strange game of orbital forensics to identify the source of the rogue signal and figure out how to work around it. It's a ghost in the machine, on a planetary scale. But the most fascinating, and debated, aspect of these orbital neighborhoods is the interaction between them. What happens if a piece of junk gets knocked from one orbit to another? This is where scientific models get really complex and, frankly, where scientists start to argue. An event in a high orbit can have consequences for a lower one. For example, some theories propose that a collision in the high GEO graveyard orbit could, hypothetically, send a spray of debris onto elliptical transfer orbits. These are long, egg-shaped paths that would cross through the busy LEO region. So, a problem that was once safely tucked away in the attic could suddenly spill down into the living room. The models that predict these cross-orbital pollution events are fraught with uncertainty. How much energy would a GEO collision release? How would the debris cloud evolve over centuries? Would the fragments be large enough to track? Different research groups have published papers with wildly different conclusions. Some say the risk is negligible, others argue it's a long-term threat we're not taking seriously enough. It's a quiet, slow-motion debate about the interconnectedness of our orbital environment. For now, you just float, suspended between these two worlds. Below you is the frenetic, shimmering, self-cleaning mess of LEO. Above you is the cold, stately, and eternal graveyard of GEO. Each neighborhood has its own character, its own rules, and its own unique brand of cosmic clutter. And you realize this isn't one problem, but many, layered on top of each other like the atmosphere of a gas giant, each layer with its own strange weather. You've explored the different neighborhoods of our orbital city, from the bustling downtown of low Earth orbit to the quiet, stately graveyard of geostationary orbit. You've seen the single relics and the shimmering clouds. Now, as you drift through a particularly dense region of LEO, a thought begins to form, a whisper of a question that has been on the minds of scientists for decades. What happens when the clutter starts to create more clutter? This is where you encounter the idea of the Kessler syndrome. And let's be very clear, this is not a Hollywood disaster movie. There is no sudden, catastrophic chain reaction that darkens the skies in 90 minutes. The reality, as proposed by NASA scientist Donald J. Kessler in 1978, is far slower, far more boring, and in a way, far more insidious. It's less like a string of firecrackers and more like a slow, creeping fog that gradually makes it harder and harder to see. Imagine you're standing in a large, empty room. You throw a single ping-pong ball into the room. It bounces around for a while and eventually stops. No problem. Now, you and a friend each throw a ball. They might collide, but it's unlikely. Now imagine 1,000 people are in the room, and everyone throws a ball. The collisions become inevitable. The balls start hitting each other, changing their trajectories, and creating a chaotic, unpredictable system. The Kessler syndrome is the orbital mechanics version of this. The theory states that once the density of objects in orbit reaches a certain critical point, a single collision can create a cascade. A satellite collides with a piece of debris, creating a new cloud of smaller debris. Each of those new fragments now has the potential to hit another satellite, creating even more debris. It's a chain reaction, but one that would unfold over centuries, not minutes. It's the universe's slowest, most boring game of billiards. You float here, trying to visualize it. You see the 2007 collision between the Iridium and Cosmos satellites. That single event, which you witnessed the aftermath of earlier, added thousands of new pieces to the orbital environment. It was a small-scale, real-world demonstration of the principle. Now, project that forward. Imagine an event like that happening once every decade. And then, as the density increases, once every 5 years. And then once a year. Each event makes the next one slightly more probable. It's a self-perpetuating feedback loop. A mainstream scientific fact here is that the kinetic energy of an object in orbit is enormous. A tiny, 1 centimeter aluminum sphere, about the size of a marble, orbiting in LEO, has the same impact energy as a bowling ball dropped from a 5-story building. Something the size of a softball carries the energy of a small car crashing at highway speeds. This is why even a tiny fleck of paint can be a significant threat, capable of cracking a space station window or disabling a sensitive instrument. The danger isn't in the size of the junk, but in its incredible velocity. Now, for a slightly more obscure and frankly, unsettling piece of trivia about this cascading problem. The models predicting the Kessler syndrome have to account for the shape and material of the debris. Not all fragments are created equal. A collision involving a satellite full of propellant might create a different kind of debris cloud than a collision involving a dense, metallic satellite. One of the weirdest and most difficult to model sources of debris is something called slag. When two objects collide at hypervelocity, some of the material doesn't just fragment, it melts and then resolidifies into strange, aerodynamic shapes. These pieces of slag can be denser and have odd, unpredictable flight characteristics, making their orbital decay almost impossible to calculate accurately. They are the wild cards in the deck of orbital debris. The great debate among scientists isn't if the Kessler syndrome is a real physical process, it is. The argument is about where we are on the curve. Have we already passed the point of no return in certain, very crowded orbital altitudes? Are we on the cusp of it? Or are we still decades, or even centuries, away from a runaway chain reaction? Some of the more pessimistic models, published in recent years, suggest that even if we stopped launching anything into space tomorrow, the amount of mass already in orbit is sufficient to continue the cascade on its own. The system would, very slowly, continue to grind itself down. Other models, which place a greater emphasis on the cleaning effects of atmospheric drag, are more optimistic. They argue that the lower orbits will eventually purge themselves, preventing a true runaway scenario. It's a scientific argument that hinges on incredibly complex variables, from future solar activity to the exact material composition of 10,000 different satellites. No one has the definitive answer. So you float here, in the quiet, and you let go of the dramatic, movie-like imagery. You replace it with the truth of the concept, a gradual, almost imperceptible thickening of the orbital environment. It wouldn't be a sudden wall of shrapnel. It would be a slow increase in the background risk. Satellite operators would see a steady rise in conjunction alerts, warnings that their satellite is predicted to pass dangerously close to a piece of debris. They would have to perform more and more avoidance maneuvers. Insurance rates for satellites would slowly climb. The cost and complexity of operating in space would gradually increase. It's the slow, boring, bureaucratic apocalypse. An orbital gridlock caused by a century of accumulated cosmic dust bunnies. The silence around you hasn't changed. The Earth below is just as beautiful. But your understanding of this space has deepened. It's not just a repository of the past, it's a dynamic system with a potential future, a future that is slowly, quietly, and inexorably being written by the physics of collisions, one tiny, high-speed impact at a time. You're suspended in this quiet, conceptual gridlock, watching the slow-motion cascade play out in your mind. The problem feels vast, overwhelming, and impossibly slow. It's easy to feel a sense of resignation. How can anyone possibly clean up a problem that's dispersed over millions of cubic miles of space, moving at 17,500 miles per hour? It seems hopeless. But humanity, for all its talent in making messes, also has an incredible, often comical, talent for imagining ways to clean them up. So, you shift your perspective once more. You are no longer just an observer. You are now a cosmic sanitation engineer, reviewing the blueprints for the universe's strangest garbage trucks. Let's take a tour of the drawing boards and test labs where brilliant, and sometimes slightly eccentric, minds are trying to solve the problem of space junk. The first and most obvious idea is to go up and grab it. This leads to a whole category of solutions that feel like they're straight out of a sci-fi cartoon. Picture this: a specialized satellite approaches a large, tumbling piece of a defunct rocket stage. From its front, it fires a harpoon. The harpoon, tethered by a strong cable, embeds itself into the side of the junk. The hunter satellite then gently tugs on the tether, slowly pulling the rocket stage out of its orbit and guiding it towards a controlled, fiery re-entry into the atmosphere over an empty stretch of ocean. This isn't just a concept. The European Space Agency and a company called Astroscale have been actively developing and testing this very technology. It's an elegant, if slightly aggressive, solution for the big stuff. But what if the junk is spinning too fast for a harpoon? Or if it's too fragile to be speared? Well, then you bring out the net. Another design involves a satellite that gets close to a piece of debris and then casts a giant, weighted net around it. The net ensnares the object, and then the satellite, or a dedicated tug, can drag the whole package down to burn up. It's like cosmic fishing. You can almost imagine the quiet satisfaction of a successful capture, a silent gotcha, in the void. These direct contact methods are great for large, single objects. They are the space equivalent of picking up empty soda cans. But what about the clouds of smaller fragments? You can't harpoon a million ball bearings. This is where the ideas get even more creative, and frankly, a bit more outlandish. One popular concept involves lasers. Very big lasers. The idea is not to vaporize the junk, which would be incredibly energy intensive and could just create more, smaller pieces. The concept is more subtle. A powerful, ground-based laser would target a piece of debris. The laser beam heats one side of the object, causing a tiny bit of its surface material to ablate, or turn into a puff of gas. This creates a minuscule amount of thrust, like a tiny, invisible rocket engine. Over time, with repeated zaps, this gentle push can be enough to alter the object's orbit, nudging it onto a path that will lead to it re-entering the atmosphere more quickly. It's a beautifully indirect solution, cleaning up space without ever physically touching the trash. Here's a fun, quirky fact about these cleanup technologies: one of the biggest challenges isn't the technology itself, but the law. International space law is a complex and murky field. The Outer Space Treaty of 1967, which is the foundational document, states that a launched object remains the property of the launching nation, forever. This means you can't just go up and grab someone else's dead satellite, even if it's a hazard. It's technically their property. So, before you can harpoon that defunct Soviet-era rocket stage, you need to get permission from Russia. This has led to a bizarre diplomatic dance, where clearing up space junk is as much a legal and political problem as it is an engineering one. You can build the perfect cosmic garbage truck, but you can't take out the trash until you've filled out the right paperwork. Of course, the scientific community is, as always, divided on the most effective approach. The debate is fierce. Proponents of direct contact methods like harpoons and nets argue that they are the only way to deal with the most massive and dangerous objects, the big, bullet objects that pose the greatest risk of creating massive new debris clouds. They contend that focusing on these top priority targets is the most efficient use of resources. On the other side, advocates for laser-based or other remote methods argue that their approach is more scalable. A single laser station on the ground could potentially deorbit thousands of small objects per year, addressing the cloud problem that contact methods can't touch. They believe that thinning out the swarms of smaller debris is the key to preventing the Kessler cascade. It's an ongoing argument: do you go after the bears or the mosquitoes? And the ideas get even wilder. Some have proposed giant, orbiting sails that would sweep through crowded altitudes, collecting debris. Others have suggested deploying a huge foam ball that junk would embed itself in. There's even a concept for a space tug that would hop from one piece of junk to another, attaching a small deorbit kit to each one before moving on to the next, like a bee pollinating flowers with doom. As you float here, surrounded by the ghosts of our orbital past, it's heartening. The problem, which seemed so vast and permanent just moments ago, now feels tractable. Maybe not easy, but possible. The quiet of space is now filled with the hum of human ingenuity. You see the silent ballet of a harpoon satellite, the gentle cast of a net, the invisible nudge of a laser from a mountaintop thousands of miles below. The mess is ours. But the solutions, in all their clever, awkward, and brilliant forms, are ours too. The silence is no longer one of resignation, it's the silence of a workshop, where clever hands are drafting the plans for a cleaner tomorrow. The futuristic hum of lasers and harpoons fades into the quiet void. The cleanup technologies, for all their ingenuity, treat the problem as just that, a problem. trash to be taken out. But as you continue your slow, patient drift, another perspective begins to settle over you, as soft as starlight. What if this isn't just garbage? What if you're floating through the greatest, most untouched museum in human history? You are no longer a sanitation engineer. You are now an archaeologist, drifting through a dig site where the artifacts aren't buried under layers of earth, but suspended in layers of orbital altitude. Each piece of debris, from the largest rocket body to the tiniest fleck of paint, has a story. It's a physical remnant of a specific moment in our collective journey away from our home world. Let's start with the big, obvious artifacts. You approach a massive, tumbling cylinder. It's an old age upper stage from the 1960s. Its silver skin is pockmarked with tiny craters from micrometeoroid impacts over half a century. You can see the stenciled serial numbers, faded but still legible. This isn't just a piece of metal, it's a veteran of the Gemini program. This specific type of vehicle was used as a docking target for astronauts like Neil Armstrong and Buzz Aldrin as they practiced the rendezvous maneuvers that would be essential for the Apollo moon landings. To look at it is to look at a direct ancestor of the lunar module. It's the space-age equivalent of finding a Roman chariot preserved in volcanic ash. A key archaeological principle, and a mainstream astronomical fact, is that the space environment preserves things in a unique way. On Earth, artifacts are subject to rust, decay, water damage, and erosion. In the vacuum of space, an object is free from oxidation. Metal doesn't rust. Paint doesn't peel from moisture. The primary forces of weathering are radiation, which can yellow plastics and degrade solar panels, and micrometeoroid impacts, which act like a slow, cosmic sandblaster. This means that objects can remain in a state of near-perfect preservation for millennia, their stories frozen in time. Now, let's look closer at the smaller, more personal artifacts. You focus on a small, metallic object glinting in the sun. It's a camera. It looks like a classic Hasselblad, the kind used by the Apollo astronauts. Maybe it slipped from the grasp of an astronaut during a spacewalk on Skylab, America's first space station. Imagine the story it holds. What was the last photo it almost took? A stunning vista of the Earth. A portrait of a fellow crew member against the blackness of space. It floats silently, its lens still pointed at the cosmos, a forgotten witness to a moment of human presence far from home. It's not junk, it's a lost diary. This is where you find one of the oddest, and most poignant, little bits of space history. One of the most famous pieces of art in space is also, technically, junk. In 1969, the Apollo 12 astronauts carried a tiny ceramic tile, no bigger than your thumbnail, to the moon. It was called the Moon Museum, and it featured minuscule drawings by 6 prominent artists of the era, including Andy Warhol. The plan was to leave it on a leg of the Intrepid lunar module. However, the story goes that it was secretly attached by an engineer, without official NASA approval. This makes its status complicated. While the lander is a historical site, the unsanctioned art piece attached to it could be considered a form of high-concept graffiti. There's a persistent, if unproven, rumor that a second copy of this tile was attached to a piece of the spacecraft that was later discarded in Earth orbit. The debate among space historians and art critics about whether this rumored orbiting tile is a priceless piece of conceptual art or just a quirky piece of litter is one of those wonderfully strange arguments that bridges two completely different worlds. This archaeological perspective forces a difficult question, one that is actively being debated in the scientific and ethical communities. If we start cleaning up space, what are we destroying? That defunct 1960s satellite might be a hazard, but it's also one of the first of its kind, a priceless artifact of the dawn of the space age. Do we deorbit it and let it burn up, erasing it from existence? Or do we try to preserve it? The concept of in situ preservation of space heritage sites is a very real, very new field of study. Some scholars argue that certain historically significant objects, the first satellite of a particular nation, or the upper stage from a famous mission, should be declared off-limits to cleanup crews. They propose creating protected orbital heritage sites, a sort of zero-G national park. But how would you even do that? How do you put a velvet rope around something moving at 17,500 miles per hour? The logistics are mind-boggling, and the debate pits the practical need for a safe operating environment against the more philosophical desire to preserve our own history. Who gets to decide what's a priceless artifact and what's just trash? Is Ed White's glove a historical object to be revered, or a non-trackable hazard that we should be glad burned up? As you float here, surrounded by these orbiting relics, you see the problem in a new light. It's not just a physical mess, it's a cultural one. You're in a museum where every exhibit is a potential car crash, a library where the books are on fire. The silent space around you is filled with the echoes of our greatest ambitions, our clumsy mistakes, and our artistic impulses. And the challenge isn't just how to clean it up, but how to do so with the wisdom of a curator, the care of a historian, and the foresight to know what stories are worth saving. You have seen the junk as a hazard, a logistical nightmare, and a museum. You've toured the concepts for cleaning it and debated the ethics of preserving it. Now, as your journey begins to wind down, you let all of that complexity drift away. You pull your perspective back, way back, until the individual pieces of debris, the rocket bodies, the lost tools, the shimmering fragments, all merge into a single, faint, human-made nebula surrounding the planet. You're no longer focused on the what or the how, but on the long, slow, inevitable then. What is the ultimate fate of this orbital shell we've built? The answer, for most of it, is a slow and gentle descent. You focus your attention once more on the very edge of the atmosphere, that thin, electric blue halo you saw when you first arrived. This is the ultimate arbiter, the patient, cosmic force that will, eventually, reclaim almost everything in low Earth orbit. This process is known as orbital decay, driven by atmospheric drag. And it is a testament to the power of tiny, persistent forces applied over immense timescales. Imagine a single fleck of paint in a relatively high LEO orbit, say at 600 miles up. For years, for decades, nothing seems to happen. It completes its orbit every 100 minutes or so, a faithful, silent traveler. But on every single pass, it collides with a few stray, incredibly dispersed atoms of oxygen and nitrogen from the very uppermost reaches of the thermosphere. Each collision is infinitesimally small, robbing the paint fleck of a truly minuscule amount of orbital energy. It's like a giant boulder being slowed down by gnats. For 100 years, the effect is negligible. The fleck's orbit might drop by a few feet. But it's relentless. It never stops. After a century, the orbit has decayed enough that the fleck is now traveling through a slightly denser part of the atmosphere. The gnat bites are a little more frequent, a little more energetic. The decay starts to accelerate. What took a century to begin now takes only a decade to progress further. The orbit spirals inwards, faster and faster. In its final years, it's dropping by miles every day. Finally, the moment comes. The paint fleck dips below the 60-mile altitude mark, the loosely defined edge of space known as the Kármán line. Here, the atmosphere is thick enough to matter. Friction suddenly becomes a ferocious force. The air in front of the fleck compresses and ionizes, heating up to thousands of degrees. The tiny piece of human-made debris, after perhaps 200 years of silent, cold orbiting, ends its existence in a brief, brilliant streak of light. A shooting star. A final, beautiful act of self-immolation. Someone on the ground, looking up at the night sky at just the right moment, might see it and make a wish, never knowing they were wishing upon a piece of industrial coating from a long-forgotten satellite. This is a fundamental and well-understood astronomical process, the slow, elegant recycling of near-Earth space. But here's a cool, slightly less-known fact about this process. The Sun has a huge say in how quickly this happens. We are currently in a period of increasing solar activity, heading towards what's called a solar maximum. During this time, the Sun throws out more energy, more solar wind, and more flares. This extra energy pumps up the Earth's upper atmosphere, causing it to expand and swell outwards. It's like the planet is taking a deep breath. This expanded atmosphere creates more drag on everything in LEO, significantly accelerating orbital decay. So, weirdly, the Sun acts as its own kind of orbital cleanup crew. A period of high solar activity can clear out low orbits much faster than a quiet solar minimum. The Sun is, in its own way, helping us with our homework. Of course, like everything in this story, there's a debate. The ultimate fate of the objects in geostationary orbit and other high-altitude resting places is a source of scientific contention. These objects are far too high to be touched by atmospheric drag. The graveyard orbits are, for all practical purposes, eternal. They will remain there, silent and unchanging, for millions of years. They will outlast every city, every monument, every trace of our civilization on the surface. Long after tectonic plates have rearranged the continents, these silent sentinels will still be tracing their patient paths in the sky. Some scientists argue that over these immense geological timescales, other, much weaker forces will come into play. Things like solar radiation pressure, the gentle push of sunlight itself, and subtle gravitational nudges from the moon and the sun, known as lunisolar perturbations. These forces might, over millions of years, slowly and chaotically alter these high orbits. Will they scatter the graveyard satellites? Will they push them into even higher, more stable orbits? Or could they, in some fluke of celestial mechanics, eventually nudge one onto a path that sends it spiraling back towards Earth? The models that try to predict orbital dynamics over millions of years are highly theoretical. It's a field of celestial paleontology, trying to predict a future that is almost impossibly distant. So you float here, in the end, with a sense of cosmic patience. You look at the Earth, wrapped in its thin, shimmering blanket of our own making. You see it not as a problem to be solved or a museum to be curated, but as a temporary feature. A transient, human-made layer on a planet that has seen mountains rise and fall, and ice ages come and go. Most of it will be swept clean by the atmosphere, repainted into shooting stars. The rest of it, the high-altitude ghosts, will become our most enduring monuments, our silent, accidental pyramids. They will be the last, faint evidence that we were once here, that we reached for the stars, and that we were, characteristically, a little bit messy about it. And so, your journey comes to a close. The concepts of orbital mechanics, of debris clouds and graveyard orbits, begin to soften and blur. They lose their sharp, technical edges and dissolve into the gentle, quiet blackness of the space around you. The silent hum of the void is no longer filled with data and concerns, but with a deep, profound stillness. You are drifting now, untethered not just from the Earth, but from the narrative itself. The Earth below continues its slow, majestic rotation. You see the deep, peaceful blue of the oceans, the soft, downy white of the clouds. It's a gentle, breathing presence. Your own breath deepens, slowing to match the rhythm of the turning planet. The light from distant stars no longer invites analysis, it's just a soft, comforting blanket, ancient and steady. Your thoughts are no longer about problems or solutions. They are simply, drifting. Like a lone, forgotten glove, you are in a state of perfect, weightless suspension. There is nothing to do. Nowhere to be. Just the gentle fall into a soft, starry dream. The slow, patient universe will take care of the rest. Everything, in its own time, finds its way home.